Welcome to the very first episode of Shop 101, a series where we take a look at all things mechanical. Today we're going to dive into differentials. We'll start with an open spool like you find on most vehicles, understand how it works, and what happens when you get stuck with one wheel spinning. From there, we're going to look at possible solutions like welding your diff, or putting a spool or a locker in, and what exactly happens inside your diff when you do that. So join me as we dive into our diff or differential and take a look at what's going on inside. So over here I have a differential and pinion gear from a Ford 8.8. Now as you can see, this differential is pretty big and it's going to be rather hard for me to explain how it all works on something of this scale. So what I did is I made this. It's a fully operational differential, exactly the same as this one, but just easy for me to explain and use. Now one thing I do want to point out is the direction of the ring gear. On my model over here, I have made the ring gear point to the outside, and on the real one it points to the inside. And the reason I did that is I need to show you what's happening on the inside of this carrier over here, and it's much easier to do that with the ring gear out the way. Now a regular differential has the ring gear pointing inwards, and they do this because of packaging. As you can see, the pinion sits on the inside very close to the carrier over here, and that makes for a small overall package which you need to operate. On my model, I've got the ring gear on the outside with the pinion on the outside, and the problem with that is the packaging would get very big. So just remember when you're looking at my little model over here that my pinion and ring gear are on the wrong side. Doesn't change how it works, but it is different on the real differential. Now the other important thing to note is just size. What I have here is a ring and pinion from a Dana 30, which is about the smallest differential that I know of, in comparison with my model, which is tiny. So this is my pinion gear over here, and my ring gear that goes onto this model. So just note the size difference. Again, just easier for me to handle the small model to show you how it works. Okay, let's start off by making sure we understand all the parts of a differential and how they work together. The first part that I want to look at is the ring and pinion. Now my pinion doesn't have the shaft on there just because I need to keep my model compact. But over here is my pinion gear and the ring gear. Now the pinion accepts the torque from the engine through the driveshaft and rotates the ring gear over there. Now something to note on the ring and pinion is that the pinion runs front to rear on the vehicle. And as it transfers torque from the pinion gear into the ring gear, it rotates 90 degrees so that it's rotating left to right. So if you think about it, this gear rotates the wheels left to right, while the pinion gear takes the engine torque front to rear from the vehicle. Now, what happens is that the torque is transferred from the ring gear into the diff carrier, this bit over here. You can see it over there. Usually that's done through a set of bolts. In my model, I've just glued it together. But the transfer of torque is from the ring gear into the carrier. Now from the carrier, the torque is transferred into this piece over here, which is called the cross pin. And you can see that the cross pin sits and nests in the housing. Now in my model over here, the cross pin was falling out, so I've actually retained it in the housing, but you can see the cross pin on the inside over there. Now on the cross shaft, they mount two spider gears, which are those little gears there. And as you can see, they are free to rotate around the cross shaft. So in my differential over there, you'll see there's the one spider gear and there's the other spider gear mounted on the cross shaft. Now in this example over here, as well as our Ford 8.8, we only have one cross shaft with two spider gears. If you've ever been racing or lifted your 4x4 into the air and spun a tire and put it down real hard, you'll know that these spider gears, just two of them, is a real weak link in a differential. The reason it's a weak link is that the total torque going through the differential, and I'm just going to use an example of 100 foot-pounds. I know it's not real and that a differential transfers much more than this, but for the sake of numbers, if you had 100 foot-pounds going through this, you have to divide that torque equally between these two gears. So each gear is going to carry 50 foot-pounds. Now in most upgraded differentials, what you usually do is you go for a 4-spider gear setup. So you will have two cross shafts, and then you'll install an extra spider gear over there and one extra one on this side over here, like that. So what happens in a 4-spider gear differential is that the load, let's take our existing 100 foot-pounds, is now divided by 4 spider gears. So each spider gear only carries, in our example, 25 foot-pounds, which is a significant reduction in load on our very weak spider gears. When I started racing my off-road buggy, I had 2 spider carriers like this one over here, and I tore up quite a few 2 spider gears. So I eventually upgraded to 4 spider gear carriers with 2 cross shafts, and never had an issue after that. So certainly if you are tearing up your spider gears and you only have 2 of them, look out for an upgraded carrier that has 4 spider gears. Now our spider gear over here meshes with what we call the side gear, like that. The side gear is splined to accept an axle shaft which is connected to your wheel. So as the differential carrier rotates, you will see it rotates the wheel like that. And that's what gives you drive through your differential. Right, so if I put all these parts together, you will see that there is the pinion, the ring gear, our cross shaft that runs across there, our spider gears and our side gears, our 2 side shafts, and our wheel end over there. And how it all works is when your engine or gearbox turns the pinion gear over there, you'll see that it rotates the differential carrier over here, and that allows the 2 side shafts to turn together. And that's how your vehicle moves forward. Now I want to just take a moment to explain diff ratios. We often hear about different ratios, 3.7, 4.1, 4.56, 4.8, 5.13, and many others. So what exactly is the diff ratio? The diff ratio is quite simply the number of teeth on the ring gear divided by the number of teeth on the pinion gear. So if we take our ring and pinion over here, this ring gear has 40 teeth on it, and my pinion over here has 20 teeth on it. So if I take 40 divided by 20, I get a 2-to-1 or 2 diff ratio. So what does a 2-to-1 or 2 diff ratio really mean? It means that you will require 2 input revolutions over here to get 1 output revolution of the diff carrier. And I'm going to show you an example here to prove what I'm looking at. If we take this input shaft over here, which is at the top, and I make a mark over here on these gear tooth over here, like this, which I hope you can see in the camera. So what you'll see with our 2-to-1 or 2 diff ratio over here is that I will need to turn this input shaft 1 full revolution, and then I'll need to do a second full revolution again before our alignment marks line up over there. So this differential requires 2 inputs for 1 output revolution, which is a 2-to-1 ratio. Now I've also made up this differential over here. It has a 56 tooth ring gear and a 14 tooth pinion gear. So if we take 56 divided by 14, we get a 4-to-1 or 4 ratio differential. Now the first thing you'll notice is that the pinion gear is much smaller than our original pinion gear over here, and our ring gear is much larger than our original ring gear. And that's typical. The higher the ratio, the larger the disparity between the different gears. So if we do the same experiment over here and we start with our ring gear in that position, we're going to do 4 revolutions. Now you'll note that you'll be out by 1 tooth. That's just the way that the numbers work out. But if we start over there with those teeth engaged, we do 1 revolution, 2 revolutions. We'll see we are now halfway, where on this one we had completed a full revolution of the carrier. That's 3/4. And our final one brings us back, and as I said, we'll be out by 1 tooth. That's just the design of this ring and pinion combination. But we have 4 input revolutions to get 1 output revolution. Now you might ask why diff ratio is so very important. In general, if you are using a stock setup with stock tires and stock diff, your OEM would have selected a ratio that probably gives you the best fuel economy for your rig. Now we all know that we like putting on big tires, and so a lot of us upgrade to 35 or 37-inch tires, and that's great. However, you almost inevitably need to do a diff ratio change if you're upgrading your tire size. I'm going to do a whole video around selecting diff ratio to match your tire size change as another episode. So make sure you subscribe to our channel, The Shop, so that you don't miss that episode where we select a diff ratio to match your tire size upgrade. So the first thing we want to look at is what happens when you're going in a straight line. In a straight line, the carrier over here and the spider gears work as a single unit, and so what you will see is we give our 2 input revolutions and we get 1 output revolution on both wheels. So if you watch carefully, the spider gears over here are not rotating on the shaft. We've given 1 input revolution and we're coming up to our 2nd input revolution over there, and both wheels have turned together and given us 1 output revolution. Right, the next thing I want to demonstrate is what happens when you get stuck. So what I'm going to do is I'm going to hold this wheel still. What that means is the weight of the vehicle is now resting on this wheel, or it's got mud on it and it can't rotate. We're still going to give 2 input revolutions over here, and what you will see is that this wheel is now going to give 2 output revolutions, and this one is going to stand still. And how it does it is that the spider gears are going to slip over our cross shaft over there. So let's take a look. You'll watch those spider gears are rotating on the shaft over there, and we now have done 1 revolution, but you can see that this wheel has done 1 revolution. And when I finish my 2nd revolution over here, you'll see we have done 2 revolutions on this wheel over here. It works exactly the same in the opposite direction. So if I hold this wheel now and I give 2 revolutions here, you'll see this one has done 1 revolution here, 1 revolution there, and when I complete my 2nd revolution here, I've now done 2 revolutions here. So an interesting thing to note when you get stuck is the wheel that's spinning is actually spinning twice as fast as what it normally is spinning. Now the reason that all vehicles have a differential is to help get around a corner. And in order to explain what's happening to the differential while it's going around the corner, I've set up this model over here. It's our same 2.1 ratio differential with exactly the same internals as this one over here. The only difference is I've put these 2 big wheels on over here. Now, I've also lined up these 2 wheels on the edge of our paper over here, and we're going to rotate this input shaft over here and allow this differential to go around the corner. Now what I'm going to demonstrate is rotating the input shaft over here and allowing the diff to do its thing as it goes around a corner. As best I can, I'll take a marker and mark out the 2 paths of this wheel so that we can take a look at the difference in distance that it covers. I also want you to pay special attention to what's happening inside of this differential. And what you'll see is that it's going to be a mixture of what we demonstrated earlier. A mixture between the carrier rotating with no rotation on the spider gears and what we demonstrated when we got stuck and the differential spun around the spider gear. So you will see that these spider gears will turn, but not quite as quickly as what they did when we get stuck. So let's get started with this demo. Right, so I'm going to rotate this shaft over here without letting these wheels slip. And what you'll see is this wheel is covering that distance. This one here has hardly moved. And we continue down this path. This wheel has now covered there. This one is still almost where it started. This wheel has covered there. This wheel has now covered that distance. And we keep going like this. And there we will see that this wheel has now done 1 full revolution, but this one over here has not yet even made half a revolution. If we keep going, we've now covered that distance. And this one here is now at a 1/4 revolution. And I don't know if you noticed it, but it just slipped over there. So we'll keep going. Keep going. And I've been forgetting to mark this one out over here. This one is now here. That one is now there. Let's keep going. And I think you get the idea. If we keep going a little more, you'll see that this one has now done 2 full revolutions and this one is only approaching its 1st revolution. So as best I can, I'm now going to mark our final position, which is over here. I'm just going to move this all out the way. So this one ended up here, and that one did its full revolution and ended there. So if we push this carrier back, I'll make a mark there. Now, watch carefully the spider gears as I bring this one back. You will see our input shaft is rotating, but if you watch very carefully there, you will see how the spider gears are rotating around themselves while the carrier is rotating in a mixture between the two motions we saw earlier. Right? So that's what happens when you go around a corner with a differential. So we marked these two paths as the wheel went around the corner. You will see that this outside wheel took this very long path, made one revolution there, then took this long path and made a second revolution. The inside wheel, however, only did this bit of revolution here, which was not even a complete revolution. We were very close to reaching our end revolution there. So if you go and look at it, the inside wheel traveled only this distance, while the outside wheel traveled almost 2 times that. And that is exactly what a differential does. It allows a differential speed between your two wheels over here, which enables you to go around a corner. So why is this differential speed important? Well, it all comes down to handling. When you're driving on a firm surface like an asphalt road, you need to be able to smoothly go around your corners. And the only way to do that is allow this diff to slip around itself, like we demonstrated over here. The drawback, however, is that the moment you get stuck with one wheel in the air or a big load on one wheel, the diff is just going to spin around itself like this and you're stuck. So how do we get the best of both worlds? If you lock this differential, what would happen is that your two wheels would now have to move at the same speed, which would mean that your inside wheel will have to slip to get past here. So if you've ever locked your lockers or used a spool on a hard surface, you'll hear your inside wheel chirping as you go around the corner, which is not desirable in most cases. So I'm going to try and explain what's happening inside of this differential when you get stuck in a little bit more technical terms. Now, if you're an engineering type, contact me offline and we can discuss it. I do understand the actual theory behind this. But what's really happening inside of this differential is this mechanism of our spider gears over here allows the torque to be equal on both of these wheels. Now, what happens with equal torque? As I demonstrated earlier, when this wheel goes into the air over here, there's no torque on this wheel. And so the differential will not put any torque onto this wheel either. The moment we can start increasing the torque over here, we can transfer torque, that same amount, to this wheel. And that's what the modern ABS traction controls do. They apply the brake to the spinning wheel over here, and however much the brake resists the spin, it transfers that same amount of torque to this wheel. And in most cases, that's enough to get you out of trouble when you're stuck. Now, if you're doing hardcore 4x4, the ideal that you would have is that 100% of the torque can be transferred to the wheel that's stuck. If you think about it, if this wheel was in the air and you could put 100% of the torque onto this wheel, then you would be able to get unstuck because it would turn and carry you out of trouble. The problem is that the differential doesn't allow you to do that. And so what people do today is they either lock the differentials, they spool them, or they weld them up. Now, there are many different ways that you can lock up your differential. You have mechanical lockers, you have electric lockers, air lockers, you have automatic lockers like this Torsen over here, and limited slip like this 8.8 over here with the spring plates in it. I'm not going to go into the details as to how each one of these different locking mechanisms work. Now, if you're really interested as to how all of these different locking mechanisms work and you would like me to go and explain each one of them to you, please go and subscribe to this channel, The Shop, and drop me a comment in this video asking for more information regarding different ways of locking differentials. It is a whole video in and of itself with all the multiple different ways of doing it. For now, we are going to go ahead and just assume that we have locked out the diff completely, and the easiest way for me to explain that is by using a spool. Now, a spool is just a machined part that connects both your side shafts to your ring gear. So I'm going to refer to a locked differential. I'm going to use my little example over here. As you can see, this does not have the differential in it. So whatever the torque is can go 100% to either side because there is no mechanism to allow slip. Now, the drawback of locking your differential, putting a spool in, or welding up your spider gears over there is that you now force both wheels to turn at the same speed because there's no more differential mechanism in there. And so if we take our example of going around the corner over here, what it means is that this path that's traveled by the outside wheel now has to be traveled by the inside wheel. And so what you're going to get is that this inside wheel starts to slip or chirp, and you'll hear as you go around the corner that this inside wheel is slipping. So what I'm going to do is I'm going to grab my big differential over here, and I'm quickly going to put in my locker over here to show you what happens. Right, with the spool now installed, watch what happens to the speed of rotation of the two wheels. They're going to rotate at the same speed, but this inside wheel is going to slip as it goes around the corner. So here we go. See how it's slipping down there at the bottom? So you're actually spinning this tire, but notice that the speed between the two is exactly the same. So like previously, there we've done 1 revolution, and we can see on this one we've done 1. And this wheel keeps on slipping. And over there we've done our 2nd revolution, and this one has done 2 revolutions. So the spool will now transfer 100% of the torque. If I lift this wheel up in the air and I turn it, both are going to turn at exactly the same speed. So as I get grip on this wheel, I'm going to push my vehicle forward. The problem with doing this is if I remove this anchor over here and I turn this, look what happens. It just wants to go in a straight line. And that is the drawback of a spool, is that the moment you lock this differential, you lose handling because it tries to push the vehicle in a straight line. Great if you're trying to climb up an obstacle, but not good on an asphalt road because you are now scrubbing this inside tire. So something that's happened to me a few times with my racing rig is I'll either push the front axle up into the air, or I'll have one wheel that lifts off the ground. And as you're driving your drive shaft over here, your differential is turning this wheel twice as fast as normal. And what tends to happen is it stores a bunch of energy, and when that wheel comes back down again and suddenly grips, it sends a shockwave through your entire drivetrain. And very often you will snap a side shaft, you will strip a ring and pinion, or those spider gears of yours will go. So something that I've learned through this whole exercise is if you do have a diff lock, make sure you engage your lockers before you lift that wheel into the air. That way your other side wheel is able to transfer the torque, and you're less likely to get that shock load going through your drive system. So in summary, your differential allows for a differential speed between your inside and outside wheel. That certainly helps when you're on the road and you're going around a corner, as it allows for relative movement between the two wheels on the single axle. And that helps make your car mild-mannered when you are on the road. Now, if you are off-roading and you have wheels in the air, you certainly need to put a locker in here. We have our Mazda RX-8 behind us. If you're going to take that out on a track and you want to accelerate really fast, what you'll end up doing is spinning one of your wheels. And once again, a locker will help limit that behavior. So certainly take a look at how you're using your vehicle and what you need your differential to do, and make a decision if you do need to install a diff lock into your diff. If you've learned something from today's video, I would appreciate it if you could help me out a little bit. The YouTube algorithm favors channels that have lots of subscribers. So by subscribing, you help increase my visibility out there, and that helps generate a few more cents. Now, I plow all of my income back into my channel, so the simple act of subscribing helps generate more content for you.
Enjoy your life. They'll try to kick you while you're down. They want to rise up while you drown. They want to fill your head with doubt. They're silently scared that you'll figure it out. I'll make it look like I'm losing, won't bother hiding my bruises. And when they finally think you're wounded, then it's your chance to be